sake of the tape, we were talking about equilibrium oxygen partial pressure with the metal and the metal oxide. We showed how to plot that up versus temperature on this scale, and then the standard, or the change in Gibbs free energy on this scale. Here's the standard change in Gibbs free energy for that metal, the red line right here. Here's the different values of oxygen partial pressure. At any given temperature, I can now predict what partial pressure of oxygen must there be to establish equilibrium. The question then is, how do I get to these partial pressures of oxygen? I put in a fuel. So we'll look specifically here at carbon monoxide as a fuel. Carbon monoxide will eat up any oxygen in that environment to get to CO2, and it will establish an equilibrium partial pressure of oxygen as well. And I can use the same formalism to put that on a graph. All right? Here's the change in Gibbs free energy for that reaction. You can see these standard state terms here corrected by the RT log of these reactants divided by the products. Has to come out to be 0. I can just do the algebra to arrange that. This is the standard state change in Gibbs free energy for that reaction minus the corrections for the partial pressure of the gas phase here, CO and CO2, and then that equals log PO2. Same expression, log RT log PO2 right there. So interesting, if I just assume values for this ratio of CO to CO2, again, I just assume them so I can put it on the graph, it looks like this. Here's one line right here for this expression over here. Here's another for different values of the ratio of CO to CO2. So I plot that up, a ratio of 10 to the minus 7, 3 times 10 to the minus 5th. The next one I can't quite read on here, 10 to the minus, I'm sorry, I can't read that exponent right there. The ratio of CO to CO2, right? So higher levels of CO2 along here, I'm sorry, that is 10 to the minus 2, 3 times 10 to the minus 5, and 10 to the minus 7 for that ratio between CO and CO2. And equilibrium is established where that intersects values of the partial pressure of oxygen. All right, so if I assume a ratio over here, I can tell you right away what's the value of the partial pressure of oxygen. Remember, I said I just assumed it. I can control that. We had a question out of Wally asked me right at the break, how do I control that? Well, be careful. It's different in a flowing system than a closed system. If you put it all in a box, you have it establish the CO2 level based on how much fuel is present. If you put it in a flowing system, you actually have a knob you can turn to control that ratio. But my point is, you establish the level of CO to CO2 in that system, and that will set a value at equilibrium of the partial pressure of oxygen, which is what we needed to figure out what happened to the metal, right? I'm looking for that partial pressure of oxygen. So here I put it all together, all right, on this lower chart right here. Remember, I was drawing this line for the metal, right there, the red line, and then I was saying it intersects some partial pressure of oxygen right at that point. So I can plot that up again and say at that partial pressure of oxygen sitting right there, what ratio of CO to CO2 must exist to give me that and have equilibrium with the metal and metal oxide pair. And lo and behold, it's right where I drew that circle. Couldn't quite move it right into the cross, but anyway, you know what I mean. Right there is the equilibria that I got for what is actually a pretty complicated system, and I can just show it to you graphically. As I said, you can get on a computer or you can find a textbook. They have these plotted up for different metals. There's a nomograph for CO, CO2. There's also one for hydrogen and water vapor. And so you can actually do the equilibria just by looking at that chart with a ruler. No supercomputer needed, right? It's probably more valuable to do it to just give you insight in terms of, well, what is actually happening? Because when you look at it, you can answer questions immediately like, not just what's the answer, but what's the partial pressure of oxygen? What happens if I do something to change the ratio of CO to CO2? You can just look at the chart and see where does that graph go, and you can see what's going to happen at the equilibrium. So it helps your intuition a lot. But if you do a lot of these, once you get the idea down, you can rely on a program like HSC chemistry to calculate the equilibrium every time with more complex chemistries. It's really valuable. But it helps when you want to do something that's fundamentally new to know what you're looking for. All right, that's why I went through all that long discussion about partial pressure of oxygen, because I just want to show you something that, well, I just thought this was very interesting and exciting, and hopefully in some time we'll turn it into an actual device that is useful to people. So I'm going to propose here some mystery metal oxide M that goes to MO2. Got a lot of M's there. It's good. We can remember mystery metal oxide, all right? So I'm drawing again an Ellingham diagram just like the ones you've been looking at. I'm adding to it now gas phase reactions, which have different slopes than the ones we've seen for the metals before, but I'm showing them here. And by the way, this is not an exact analysis, or let me put it this way, it's a restricted analysis because I'm considering the case where I have 1 atmosphere of CO, CO2, hydrogen, water vapor. It's just to give you the idea, right? If you want to correct it for different values, you can move these lines around just as we explained to correct for different ratios there. So this is the idealized case. It's a restricted analysis, but you're going to see it turns out to be kind of an important one. So this is an Ellingham diagram, and if a metal sits up in here, all right, if you draw the oxygen lines are going to come down like that, the metal line is up in here, the oxygen partial pressure is, can you remember, is it high or low? It even says on the slide, right? It's high, right? If the metal line goes up in here, you have a high oxygen partial pressure at equilibria, and it will burn any of these fuels below it, right? Because that thing's going to sit in there at that temperature. It's going to be pushing out oxygen, and you can see this one needs less oxygen partial pressure to oxidize CO, for example. Does that make sense what I just said? So up above this line, everything will get burned if you have a metal sitting up in here, all right? There are metals like that. You know, silver has a very high oxygen partial pressure, you know. I think silver sits like way up in here, right? So it'd be really great chemical looping carrier, low temperature, right? So there are metals that would sit up there. There are also metals that are way down here, all right? Any metal that's, the line is going to go up in this direction here. So the oxygen line is going to come down here. You'll have very low oxygen partial pressure. The oxygen partial pressure at equilibrium is so low, it cannot oxidize methane, carbon, hydrogen, or CO. Right? That's why I shaded these two regions in the way that I did. Again, that plot will show you where's high and low oxygen partial pressure depending on whether you're down here or up here. Now, here's an interesting question. What if I had a metal that was sitting right here? Here's the metal, the mystery metal plus oxygen going to MO2. So the standard change in Gibbs free energy is coming this way. The RT log of PO2 is coming down this way. Notice the axis doesn't go all the way to 0 here. That would go right up to 0 degrees Kelvin, minus 273. But anyway, I made it bigger so you could see it. So there's the oxygen line coming this way. The metal's coming this way, and they intersect at this temperature, 1000 C, right at that point. Well, that's an interesting metal, all right? It reacts with oxygen according to that Ellingham line, that red dot. How does it react with each of these reactants? Remember, just look at the chart. This is not a trick. I'm saying combustion here, inert here. Look at where the different fuels are, methane, carbon, hydrogen, and CO, relative to where that dot is. How does this material interact toward equilibrium with methane? Make sense? Not a trick question. It will burn it. It has a higher oxygen partial pressure than that line needs. All right? Does that make sense? How does it react with carbon? Here's carbon line down here. It has a higher oxygen partial pressure than that guy needs to get to CO. All right? Are you still with me? Right? How about hydrogen? That's interesting. Lower oxygen partial pressure. How about CO? Lower. Well, that's really pretty interesting, right? Because what I just told you, I mean, so what? All right? It will oxidize methane, it will oxidize carbon, but it won't touch hydrogen and it won't touch CO. You know what that's called? a miracle. You know? It reacts with solid fuels to create syngas, hydrogen and carbon monoxide. That's gasification without any oxygen. All right? This isn't, I joked it's a miracle, right? It's a miracle we found it. It's a well-known fact that they exist based on Ellingham diagrams, and there are a couple of metals like this, all right? I think ceria will also fall into this category, but just didn't want to build a gasifier with ceria. The things that we found most recently here, this is a 2016 paper, calcium ferrite. I mean, you dig stuff out of the ground and grind it up and heat it up, you'll end up with calcium ferrite, right? Very simple material, and it will oxidize solid fuels right to synthesis gas. So I'm just, I show you this just to show the power of understanding the physics represented by that Ellingham diagram, right? Because now I can understand, I mean, that's how we came to this. We were running tests and we were just looking at calcium ferrite, and my colleague Ranjani Sarawarden and Henjin Tang and Jarrett Riley, Ranjani kept bringing me this data, says, this is crazy. We have all this syngas coming out and we're consuming all the carbon. And Ranjani and I were debating about kinetics and all these complex things, and finally we just sat down and looked at an Ellingham diagram and like, it's right there. It's right in that part, doing exactly what you would expect it to do just based on equilibrium considerations. So that's kind of an interesting finding, and as I said, Ranjani keeps beating me up like, Gio, you got to build a reactor for this and turn it into a gasifier. I said, I know, but we're kind of busy right now. But anyway, you know, we thought that was really an interesting finding because of understanding the thermodynamics. So you see what I told you? Thermodynamics, it's great stuff, right? Go read those textbooks. You, me, and the other guy mentioned, we'll have lunch together and talk more about it. So anyway, so here's your little quiz. See if I communicated anything to you today. All right? So you go home to your home institution and you're talking about, oh, I heard this talk on chemical looping. The guy was kind of confusing and didn't really follow what he was saying, but boy, there'd be a market if I'd come up with a better chemical looping carrier, right? It'd be really great. And I know that aluminum burns with a lot of energy, right? You ever burn aluminum, see aluminum burning? It's pretty hot stuff. Maybe I should propose making an oxygen carrier out of aluminum, you know, aluminum oxide. So take a breather. Good idea? Bad idea? How would you argue that from your experience? Forget about what I just told you. How would you argue from experience? Is that a good idea or a bad idea?
Bad idea.
Yeah, how come?
Aluminum is really inert.
It's aluminum to alumina is extremely exothermic, right? Where does it fall on an Ellingham diagram? Go back here. It's probably off the bottom of the chart right down in here somewhere. It comes up like, maybe if you got it up to, I don't know, 2000 centigrade, you might be able to reduce it. But it's pretty inert stuff. You make refractories out of it, right? Remember, the development of aluminum was stymied by the fact that they couldn't figure out until, Charles Hall came along and developed the Hall process, because they were trying to reduce aluminum oxide thermally, and you could never get the oxygen partial pressure low enough with conventional fuels, like how you make iron, right? So Hall came along and realized electrochemically, and that's how we make aluminum today, right? Because you can put in a lot more potential to pull the oxygen out electrochemically. That's why you make aluminum electrochemically, and then at the flip side of that, that's why you make steel thermally, right? Because you can do it with a fuel directly. So this was just a check to see this question here. You know, you kind of get the idea of the Ellingham diagram. If you have materials that are way down on the bottom, to get those things to reduce, you really got to pull the oxygen, and you just can't do it with a fuel, right? Because the fuel lines are further up on that chart. The partial pressure of oxygens are still too high, so you go electrochemical route. Okay, and then also you just argue from your experience, you know, alumina is a refractory. Exactly, good point there. Okay, we got to talk a little bit about solid carbon formation, understand chemical looping. You know, if you have this chemical looping system where the fuel is reacting with the metal oxide in this region, what happens if some carbon actually makes it out of this region and gets into the air reactor? Air reactors at high temperature, air, carbon, mix CO2, right? The very thing you were trying to like avoid and keep it isolated. So you can't afford to have carbon forming on that surface and then getting carried over into the air reactor. You can't have any leftover solid carbon make it through. So in fact, in our lab, we're looking at, and others as well, looking at devices to make sure any leftover residual solid carbon gets kicked back into the fuel reactor. And then you also need to be sure when you're operating the thing, you don't drop into this region where you can have CO go backward to CO2 and solid carbon. So you need to know where this line exists. It's again just an equilibrium that you can look up in a textbook of where carbon forms versus where CO or carbon is actually gasified to CO. So you want to stay away from low temperatures with high levels of carbon monoxide, or you'll form solid carbon. And that's useful just to know for general combustion engineering when you're working with fuels in a hot environment, right? You want to stay away from where you're making solid carbon. It's basically soot, right? So that chart might be useful to you just to take a look at. I would encourage you to look at the conditions in the text that I cite there. That's at 1 atmosphere. Let's talk about the oxygen carrier. This is pretty straightforward from here on. If I'm actually going to carry oxygen, I need to know how much oxygen can I put onto the carrier, and what does it actually mean to convert this fully reduced species like copper or iron over to a fully oxidized species. I can define a conversion between 0 and 1, that capital X right there, and somewhere in between the mass that is still, here's the totally oxidized state minus the reduced state, there's the mass of the thing versus the reduced state. So you can take the conversion back and forth between those two extremes, and that's how you speak to, well, how far have I reduced this material in the process? So just some nomenclature. By the way, I noticed when it printed in your copy, the chi ended up printing as a C. So you might correct that so you don't get confused, 100 years from now if you pick the notes up again. Write down in here, your printed copy, the chi come out as a C, I noticed. But anyway, it is significant to understand kind of the magnitude of these different conversion parameters. And so on this axis, I'm just showing graphically, typically you might convert from, well, I didn't fully oxidize, nor did I fully reduce the material. I'm sorry, I said it the wrong way when I referenced that. Didn't fully oxidize, didn't fully reduce the material. So there's some working delta, conversion that you would use as this material is cycling through the system. And it's interesting to notice kind of the scale of these quantities here for a typical carrier. This is the fraction of the material that might be inert, right? If I make a material as an oxygen carrier, you might have 50% of it being a supporting material, and then the remainder of it is the working material, and then of course only some part of that is oxidized and reduced, the amount of oxygen going on and off, because it has the other cation sitting there that you're sticking the oxygen on and off. So when you actually look at the mass of material that is oxygen on the carrier, it can actually be a very small number. How much oxygen can you get on or off that material? And then if you put it furthermore on an inert support, you're circulating on a material that is not working oxygen. All right? Let's take a look at how big that is. So for iron being reduced to its first, the next lowest oxide state, hematite to magnetite, there's like 3.4% of the mass of the iron comes off as oxygen. So you think, there's not much oxygen available. You start thinking, I've got to circulate a lot of material around to supply oxygen. You're right. Maybe I should look at something else. Well, copper is pretty good. 20% of the mass of the copper oxide comes off to give you copper, comes off as oxygen to give you copper. So you end up with, okay, I'm starting to talk about maybe a little bit better concentration of oxygen on that material that's flying around. And then if you go to the sulfate system, calcium sulfate to sulfide, almost half of that material is oxygen when it starts as the oxide state and then you reduce it. Like, wow, I like that. It's cheap too, right? Lots of calcium sulfate. So you think that might be a really good one. So how much do I need to circulate? I said that might not be a lot of oxygen on that material. Well, what do we know about technically circulating large volumes of hot solids? There's two analog technologies to chemical looping. Fluidized bed catalytic cracking, FCC processes. You take, it's actually a catalyst. It's not an oxide, reduced oxide system. You take a catalyst, and let me see where the hydrocarbon goes in here. It goes up this reactor with some stripping steam. You form a bunch of carbon on it. You're taking carbon out at that point, and then you get the lighter hydrocarbons out of the top. That's how it cracks the stuff. And then you actually burn off the carbon and it goes out as flue gas in the other reactor, and you keep recycling that stuff around. Fluidized catalytic cracking, the chemical engineers just love this stuff, right? That's their whole business, is improving things like that. It does have very large solid circulation rates at temperatures almost comparable to what we do in chemical looping. So you look at it and think, well, seems like I could make a process out of that. Look at the circulation rate. That's the largest one that I could find in the literature. 41,000 kilograms per minute of solids flying around, right? 41 metric tons every minute. That's a lot of material to go around. So if I take that as like, well, there's an example of very high flow rate, and take that as my upper limit, and then I calculate out the thermal output for a steam power plant, what kind of circulation rates do I get, making some assumption about that fraction of conversion? Remember I said on the carrier, what do I get? Let's just say I'm, I don't know, maybe converting 80% of it or something like that. The thermal output of the power plant, 200 to 300. For different oxygen carriers, you start to see kind of the level of thermal output that you could achieve at that maximum flow rate. It's in the range of power plants that we want to build, all right? That's shown here. It's also shown, schematically here for these different carriers. If I had a lot of, oxygen capacity, I can get up to higher thermal outputs and still stay within that 41 metric tons per minute, right? Again, what I'm telling you is there are devices built that have this type of solids flow rate at these conditions. If we think about it and then say, kind of convert it to chemical looping, we can get to the kind of thermal output for most of these carriers that we're interested in. So it's to check, I think I can build something like this from an engineering standpoint. But there's more to the story than just oxygen capacity. I'm going to take you back to what we started with, talking about the endothermic and exothermic carriers. Let's focus just for a minute on endothermic carriers. Remember those carriers, you need to put heat into the fuel reactor. Otherwise, it'll just quench the reaction, right? It needs heat to sustain that reaction. And I said, the only way I can get that heat in there, I can't put a steam pipe in, is I bring it over with the carrier. It's hot, and I'm going to let it, the sensible cooling will provide heat for the reaction itself. So I've got to have a carrier circulation rate to consume the fuel, and then for endothermic carriers, I need to bring heat over there. So there are two different requirements setting the circulation rate around that loop. How do they compare? That's the question. It turns out that the required circulation rate is sometimes entirely dominated by the need to supply heat, this criterion. So in that case, it doesn't really matter about oxygen carrier capacity. That oxygen carrier is just bringing heat over. So I'll show you this specifically in just a second, okay? But does it make sense? If I got to put heat in there, I might just need, I could throw rocks in there for that matter, right? And that's what I need. I need to bring the heat over. So, a lot of people in chemical looping, like, oh, I got to have a better carrier, I got to have a better carrier. Stop and think a minute. Do I really need a better carrier, or am I really just managing the heat? If it's endothermic, I tell you, you're probably managing heat. Let's take a look. Circulation rate analysis. So I've shown the loop that we've looked at before, but I've just kind of, highlighted out all the details here to where it's just an air reactor where I'm taking heat out of the reactions there, and then I'm showing two different circulation rates, bringing that carrier back around to the fuel reactor, and it loops around. Two circulation rates, A and B, and there's actually only one, but I'm showing it here as A and B to emphasize these two conditions. I've got to get enough oxygen over into this region to react with all the fuel, and at least for the endothermic carriers, I've got to supply enough heat, bring it on over into that reactor with the carrier. So which of those two numbers is bigger? Well, let's take a look for some specific carrier pairs. So if I take, my quantity A here is the circulation rate I need just to supply oxygen to burn up the fuel. That's this column right here. This is the particular carrier pair, meaning the oxidized state and the reduced state. So for iron, you go through several different reduction states to magnetite, to wistite, and then finally to iron. Those are the different oxide states starting from the top here at hematite. And you can see that R0 quantity, oxygen carrying capacity, remember I said it's only like 3.4%. So for that particular carrier to supply oxygen to burn up the fuel, all right, you need to supply 2.35 kilograms per second, the minimum circulation rate of oxygen, over into this reactor over here. If I have more oxygen carrying capacity, I need to bring less over, all right? If I keep driving up the oxygen capacity by reducing it down, I need to bring less oxygen over to supply the fuel reaction. This was all done for like a kilogram per second of fuel, by the way. I forgot to point that out. I'm sorry, a megawatt thermal equivalent of fuel. So then I get down here to the calcium sulfate. This thing, remember, has lots and lots of oxygen capacity. All right? Half the stuff coming around with that carrier is oxygen, and looky, I just barely need to supply any in that circulation to burn up that fuel. So it all makes sense. You know, depending on how much oxygen I get off the carrier, I can reduce the amount of circulation. That was if I'm just supplying oxygen. How much do I need to circulate to keep the heat within 50 degrees centigrade? I'm bringing the stuff over. That endothermic reaction is consuming heat as it oxidizes the carbon. All right. Well, for iron, that circulation rate actually needs to be a little bit higher than the amount you need just to supply the oxygen. As I supply more and more oxygen, I keep, I'm needing to drive a reaction even further, and so I end up needing to supply more just to keep the heat up. It keeps going as we go down here to the next state. Copper oxide is an exothermic reactor, an exothermic reaction in that reducer. I don't need to supply any heat. The only thing I need to do with copper oxide is circulate around to give it oxygen. Remember I said that before when we get in the lab? It's really easy to run that one. Look at this one over here, calcium sulfate, sulfide, that ratio is quite a bit higher, that quantity, that circulation rate, 3. So I take the ratio of A to B, that's the ratio of the circulation rate I need to keep the heat up at this level versus just to supply the oxygen. Lo and behold, I get down here to this carrier I thought was just great because of its oxygen capacity. It is great in terms of oxygen capacity, but it needs a lot of heat to pull all that oxygen off because it's endothermic in that reactor. So my circulation rate ends up being determined dramatically by the need to manage the heat. You're circulating all that stuff around not to supply oxygen, just to keep heat in the reactor. Now, there's some pros and cons here, right? Because I also don't have to reduce very much of that oxide state if I'm circulating a whole bunch of it, right? So there's big trade-offs in terms of how you'd set one of these reaction systems up. So my point today is, if you get into this area, remember the thermal management and the management of the oxygen are the two things that you have to play off together. It's not just one or the other. Sometimes it gets lost and people say, I'm going to give you a better oxygen carrier. If I'm using my oxygen carrier for thermal management, you can give me a rock and I'll be happy, right? And that's what you do with the inert support. So that can be your carrier for the thermal energy and balance that with the oxygen coming off of, say, like a copper carrier, which is actually how we do one of our own. So, well, let's look a little bit now. We've talked about thermodynamics. We've talked about just basic balancing of thermal energy in one of these chemical looping systems. You also need to know something about kinetics, right? Determines how big is it going to be? How big do I have to have a reactor? It's an interesting problem. If you think about how to just do an initial sizing of the reactor, so you might look at this as like a bubbling fluid bed, right? So you have this fluid bed of material and the material circulating almost like a stirred reactor. So you can treat it like a stirred reactor with inputs coming in one side, going out the other, certain volume of that reactor. If I know something about the kinetics in this process, I can write out the balance equations and can actually solve, well, how big do I need it to be to get the conversion that I'm interested in. To actually do that, you need to know something about the kinetic rates. So for solid systems, it's always a challenge to get kinetic rates. There's a lot of complications, but the easiest way to get those rates is to put the material into a thermogravimetric analyzer, or TGA. So you load the material onto the pan, and it's actually measured as a balance, run it at temperature, put the reacting gases over it, and then measure the conversion, just as we described it a couple slides back here. If you have a gaseous fuel, you can just cycle the fuel or oxidize over the sample pan, and you get a whole bunch of cycles to analyze. Does that make sense? You put it in there, it's sitting in there, maybe starting in the oxide state. You put fuel in it, and it starts to release the oxygen, and then the weight is being reduced as that oxygen coming off. You're measuring that, and so you're measuring the rate that that material is being reduced. As soon as it reduces fully, you can introduce oxygen, and the weight will start to go up again, right? And you can measure that rate as well. So that's how you get the kinetics out. Very straightforward for, gaseous fuels. Guess what happens if you want to do coal? Oh, it's very time consuming, because once you consume the solid fuel, you take the pan out and refill it. So it's a bit of a challenge, especially if that coal has ash in it, because the ash is left over with your carrier. Pretty soon you have a pan of ash and carrier. You don't have any room for the fresh coal. One of our technicians, who's very patient, actually separated them out manually. Yes, question?
How do you actually do that? Since for TGA you have to have, if you have the metal, for example, you're putting in, say, CO or CH4, the reaction can proceed. But if you have coal and the metal oxide, how did that happen in the TGA?
I'm gonna repeat that, because they may not hear it on the audio. The question was, well, you can understand how you would do the carrier reacting with the gas phase, but if it's a solid, how in the world does it react? You just set me up for a couple slides ahead, so keep that thought. We're going to answer it directly. So stay tuned. We'll get to that in just a minute. So this is an example of some data from those TGA tests. The plot that you're looking at with the red squares, this is gaseous reduction and oxidation steps for a particular carrier we're interested in. Whoop, got to go back here. All right, so here's the mass measured, what's weighing on that pan as you go through cycles where you reduce the material, and then, there's a brief period here where you're letting it just relax and then go back up again with oxygen, so it reoxidizes again and again and again. And so you can see this is a wonderful material. There's no change cycle to cycle. Very much repeated every cycle. For an oxygen carrier, you can't afford to have the thing degrading over time. Right? You got to have that oxygen capacity maintained. So you do that enough times, then you can plot up the conversion as a function of time at different temperatures, and then back out a kinetic rate expression. And there are a number of these in the literature. I just included one. I thought it would be fun, though. You can think about the kinetics measured in a TGA pan, but this is a lot more interesting to just see it physically yourself. So what I'm showing you here is a propane torch. And I have a picture of the flame right there. And now we're all combustion engineers. Don't be embarrassed here. But what type of flame is a propane torch? Is it premixed, partially premixed, diffusion flame? What is it? Propane torch. Just take a look at it. Anybody know right off the top of their head what type of flame? It's premixed, and if you run it the way I have it here, it's actually partially premixed, because you can see, there's the inner surface right there, but then it's entraining air from the outside to complete combustion in that broad flame. If you run it if you turn the thing way down, you'll see it'll go a fully premixed flame. If you run it hard enough, you'll see two different distinct flame zones there, so it'll be partially premixed. So I'm running this thing partially premixed, so right in here, you're still getting oxygen reacting with fuel from the environment. So here's your quiz from our earlier discussion of Ellingham diagram. In this region, just roughly, what's the partial pressure of oxygen in that region where you've still got fuel left trying to get to air? Is it high or low? Partial pressure of oxygen inside of that reaction zone, high or low? It's low, right? It's trying to get oxygen in there to oxidize that fuel. So you have low oxygen partial pressure in that part of the flame. So I can get a propane torch and I can create a region of low oxygen partial pressure and high temperature, which is exactly what exists in the fuel reactor for chemical looping. So what I did was I just took 2 copper wires, just so you could see 2, and then behind them you can make out a temperature color chart. All right, so you know kind of, well, what temperature are we talking about? If you don't have a good eye for temperature on hot metal, if you have a hobby like people gunsmith, they can look at metal and tell you it's that temperature within amazing precision. But anyway, so that's like up in here is around 800 centigrade, that, you know, red, orange. So you can just look at this and see the kind of temperatures we're operating are right in the same range as chemical looping, 800 centigrade, as that torch hits those things. Now what I'm going to show you when I turn the video on, we'll kind of move this around. Look right in here and you can see that copper has a different character than what's out in here. So simple question, copper versus copper oxide, which is shiny? Copper versus copper oxide. Just think about a penny for a minute. Right? Copper, right? Fresh new penny is copper and it's shiny, and as it oxidizes it gets dark. All right? Or copper pipes, maybe in your home or your apartment, right? You'll see them after they've been there a while, they oxidize, they get dark. So when you look at this, it's really quite instructive. Watch the image there of the flame playing around on the surface. You can see the difference in color right on the surface of the copper. It's shiny in that reducing region, and as that thing is moving around, it oxidizes where it hits the air, right? It turns to a darker color. Is that fun or what, right? I mean, you can literally see it, and so you know the kinetics are pretty fast, right? I mean, on the slide I showed right before this one, I was showing you the TGA data, and you can see, even on that TGA pan, as soon as you introduce the oxygen, you get the oxide state very quickly. And so I hope what I showed you is a correct interpretation of what I'm seeing with my eye, but it really should be, right, based on what I'm showing you right here. It's the same set of conditions. I'm getting this rapid conversion between the oxide state and the reduced state. So kind of an interesting just example there of what the kinetics look like. I'm going to speed us up a little, so I'm going to skip a couple things here. I'm not going to speak to this next 2 slides on the kinetics in a reactor other than to say these systems can exhibit light-off behavior like any conventional combustor. Just write out the balance equations. You can get the same kind of classic S curve that Professor Zhu talked about. You know, they can exhibit light-off under some conditions, but not all. Why is that important? You don't want to be the researcher that's sitting there trying to get the thing going, and you suddenly move the reactor over to light-off condition and create a large vat of molten carrier, right? So you just need to think about that. It depends on the kinetic rate, it depends on, you know, the operating conditions, but they can exhibit that type of light-off behavior. So we'll skip the details of that. One thing that's important, I talked about measuring kinetics. Well, how fast do you need the kinetics to be? I mean, think about that, right? I mean, there's some number that I just measured. Is that good enough? Well, I'm not going to go through the math on this slide because I went over it several times and I thought, I'm just going to jump right to the end because I think you guys will get the point rather than following this through specifically. But the active density of material right here, that's how much material that reacts inside of the vessel per unit volume times the specific heat of its reaction times that conversion rate that I measured in my TGA. That's going to give me the thermal output of the reactor per unit volume of that reactor. I want to build something that looks like what I'm familiar with. So if I go through in a textbook and look up values that fit into this expression, I find out I need an active density that's something like 2% of the total bed volume. Now this is an interesting point because unlike single-phase combustion systems, I can change the active density that's inside of that volume just by pushing more material into that same volume up to the point where it's completely full. So if I have particularly slow kinetics, I'll just stick more stuff in that volume up to the point where I don't have any more room. But you know what I'm saying, right? I have this gas phase that I'm reacting with. If I put just one particle in there, my reaction rate is controlled by that individual particle. If I put another one in, the reaction with the gas phase just doubled, and another one, and another one, and another one. My point again here on this slide, you can adjust that active density in these heterogeneous systems. So when you say, well, I need the kinetics of this problem, yes, you do. You absolutely do need them. But don't forget, the actual reaction with the gas phase is also determined by how much of that material is in there. Right? So you have this extra knob in your design that you can actually use. So it's different than if you're doing like a gas phase combustor design or something like that. So very different when you look at these heterogeneous systems. So let's get to the question why you asked. I didn't say your name right. He asked me again about like solid carbon. How do you do this? Let's take a look at this. This is really an interesting story. Can you use the solid coal directly? All right. So again, I'm showing you the TGA profile here. This is the weight on the pan here in the black line. This is the reaction temperature. And what we've done here is loaded the pan up with coal, in this initial case, just with coal, and we heat it up. The blue line here is the temperature ramp inside of the TGA profile. All right. So I'm raising the temperature up. You can see the mass that's sitting on that pan drops as you drive moisture off of the coal. As you drive the coal volatiles off, it comes down right up to this point. And what you're left with is the solid carbon left on the pan that's just there. It won't react with nitrogen. And then I turn on oxygen into the TGA and I burn the rest of that solid carbon off, and I'm left really just with the ash from the coal. So that's sort of conventional combustion in air. First a pyrolysis step and then combustion with oxygen as you drop down to that point. Now I take the same pan, I load it up with coal as well as, in this case, a copper oxide carrier, and now nitrogen gas in the background. So there's no oxygen coming from the background gas. It is exactly the question that was raised just a few minutes ago. How do they react together on the pan? Well, you bring the temperature up, and now compare this black curve with the oxygen carrier to the one where I just have nitrogen on the pan. Boy, you see immediately I'm consuming, pretty much everything, right? I'm down, with no oxygen in the environment around, I'm down to that same level. So clearly I'm getting the oxygen out of the oxygen carrier. And I consumed all the carbon, and hydrogen that was in the fuel. And then when I introduce oxygen, what happens to the weight? Well, I just reduced all the copper, so I reoxidize it. Now it goes back up again, right? As I reoxidize. So that's right where, okay, if I wanted to do another test with that carrier, I have to take it out and reload it with more coal. Physically, how does it happen, right? There's no gases involved here. I've got this nitrogen, no reactive gas, I got nitrogen. Well, there's a couple ways it can happen, right? But it just bugged me, certainly, because when we did this the first few times, we didn't expect the rates to be very high. We thought, well, surely what has to be happening is any moisture that's in the coal is going to gasify a little bit of the coal as it's coming out. Once it gasifies that coal, the gas phase can react with the copper oxide. That'll produce more CO2 and water that can then serve as a gasifying media. That's pretty much how most people really thought the physics of this happened. And that's true. That does happen. All right? It's a part of the process. But we weren't satisfied that the rates matched our understanding of those processes. The gasification rates just didn't seem like they'd be fast enough at these conditions. So what in the world's going on here? So coal reacting with metal oxides, as I just said, you get coal, you get pyrolysis products. Those pyrolysis products include syngas. That can react with copper oxide to produce the product, hydrogen, water vapor. That stuff can actually then go through and participate in gasification of the remaining carbon. Here's gasification with CO2 to give you CO. You can have CO2 then in the background going through several routes to give you more CO or CO2. And then finally, with copper in particular, the equilibrium pressure of oxygen at those temperatures can actually separate out the oxygen just by heating it to provide gas phase oxygen to react with the coal. Those are all the mechanisms you typically see people referring to when you say, I'm going to do chemical looping combustion of solid carbon. But there's another one, and that is the direct interaction of the metal oxide with the solid. And when we did this, this is now several years old, I don't think we believed our own results, and because there weren't many people talking about a solid-solid reaction in these systems. And it seemed foreign that you would consider it. But there are a lot of systems that are solid-solid reactions, right? And very fast ones too, right? You ever see thermite reaction? They weld, you know, railroad tracks together with thermite reactions between aluminum and magnesium and iron. I mean, it makes this mixture. It's quite impressive, solid-solid reaction. So why couldn't it happen here? So what we did is we went back into the lab on a TGA pan. We said, well, let me go back to my Ellingham diagram and take a look at copper going to cupric oxide and releasing its oxygen. At 500 degrees C, I can go look up in that book, what is the partial pressure of oxygen? 1 × 10⁻⁹ atmospheres. So very low oxygen partial pressure. So we put some carbon in a TGA pan at 10⁻² partial pressure of oxygen, 1% oxygen. Let it sit there. Nothing happened. Didn't react hardly at all, right? You're saying, okay, I'm going to decompose copper oxide to give me oxygen at that partial pressure. Is that going to explain the reaction with carbon? No way. I can just put oxygen at that level and I couldn't get a decent reaction. Yet when I mix the copper oxide in with a coal and react them, they go very quickly. That's why we thought there's something else going on here than what we understood. So we went in, like I said, put that together in a pan, and gosh, there was a lot of reaction going on. So what's the explanation? Well, we went in and actually did the same test with different size particles for the oxygen carrier. Well, different size particles mean higher levels of contact, physical contact, between the carrier and the solid carbon. We'll just take a look at the graph, what ended up happening. It's a TGA profile again, temperature up in here. Here we're showing reaction rate, the derivative of the rate of change of the mass. And so you see as we start to shrink down the particle size, we get at lower temperatures even higher and faster reaction rates. Looks like there's a solid reaction going on there. So just to make sure, we said, well, let's take one size particle and then we'll just dilute the material with some quartz particles so you keep the same size particle but separate them. And lo and behold, as we add more quartz just to keep the particles apart, you end up shifting the reaction to higher temperatures with less conversion. This was without any dilution. This is as you start to dilute it, you get up to that level. So the point is, all right, in addition to this data as well as some DFT calculations, there really can be a solid phase reaction between carbon and the oxygen carrier. Just solid reaction. And this is other people who looked at this same conclusion. But you think, well, what good is that practically, right? I have to build a very large one where the material is in a fluid bed. They don't bump into each other hardly at all, right? So who cares about that? I do. You know why? Remember I talked about carbon deposition on the carrier? I'm worried about that stuff coming out in the air reactor. You know what this is telling you? Don't worry about it. I can have coke trying to form on that carrier. As long as it's in the oxide state, it will keep oxidizing it, right? Because it comes directly out through solid contact. So it's very important from that standpoint, physically understanding, okay, that's at least one thing I can check off. I'm not worried about it anymore because I can get that reaction to occur between the solid phase carbon and the oxygen carrier. So it's a very nice finding, you know, early on as we started looking at this, that maybe I don't have to worry about coking so much. And frankly, I wish some of those guys who are doing FCC catalysts would put a metal oxide in there. Actually, I think some of them are, because it'll take care of their coking, right? I mean, just oxidize it. When they go out to take the oxide state, it'll reoxidize the metal. So let's shift gears now and talk about how we would actually design one of these. Let me make sure I know when the next break is. Does anybody know off the top of their head? 16:15 in my world is 4:15, about 10 minutes from now. That's good. Reactor design and system issues. You're going to learn everything you ever needed to know about fluidization in 10 minutes, all right? Guaranteed. So get ready for a ride here, all right? Fluidization, widely used in the chemical industry. If you do maybe some consulting, you end up working with some chemical engineers, you got to know the basics here, and that's what you'll get here today. So the main topics listed right there, we'll jump right into them. This is key to understanding chemical looping combustion. If you discover you have to work these issues, 2 references you must get are there on the slide. You'll find them easy to read, and you'll have lots of data in the book by Basu that's like practical data if I need to do a design. So fluidization is really quite fun. A granular material, you know, doesn't typically flow like a fluid, right? Sand just sits there. It doesn't flow by itself anywhere. But if you put it in a container and you pump air through a mesh at the bottom, it will fluidize. The volume increases, the space between the particles increases, and if you tip that over, it will behave like a liquid. It will form a level surface in there. It's even more interesting if you punch a hole in the side, the material will start flowing out of there like a fluid. Or if you put a weir in the middle of the device and you initially start with these two surfaces not being even, if you wait just a second after you fluidize it, they will come and equilibrate just like a liquid fluid. That's why this stuff's very easy to understand if you just go back to it's a fluid. It's not solids and gases. It's a fluid once you get it in a fluidized state. So it's interesting to also consider, well, what happens like a fluid when I put something that's heavy in or something that's light? Something that's heavy will drop to the bottom, and something that's light, lighter than that density of the material, it'll pop to the surface. All right, so it makes stuff float or it makes stuff sink depending on its density. So there's some parameters that'll be useful. The void fraction, we won't get into the details here. The superficial velocity, that's the velocity of the gas through that volume as if there was no solids in there. It's what typically people will refer to when they talk about the velocity of fluidization. Just imagine the volume wasn't there. And helpful to know, the pressure drop through the bed balances the overhead weight of the material. Once you understand that, you can really see a lot about what is going on in fluidization. It's just like a column of fluid, right? So the pressure at the bottom has to balance the weight of what's above it. It's important to understand that when you think about laying out a fluidization system. So we're just going to skip a slide there and just take a look at this because this is just fun. So here's an example of, it's the same fluid bed just shown twice here, but we have the bed of sand right here. It doesn't have any fluidization gas going through it. And then we buried a rubber ducky inside of that bed of sand on that side. And then there's a piece of metal that we just had laying around the lab, stuck it on the top of the surface there. And we're going to show you what happens when you turn the air on to fluidize these. What should happen, right? No surprise. Yeah, boom. So it's just fun to actually see it for real happen. Whoop. Didn't quite get there. How do I get to there? Please play now. Oh, I don't know how to turn this on. There we go. Okay. So you see the metal just drop down in, and if you're patient for just a second, boom, up comes the rubber ducky, right? And it will float on that surface. Now this is fun to watch, but it's practically extremely important, right? Because in a fluid bed, you can sort materials out based on their densities, right? Some will sink and some will rise to the surface. Becomes very important when you're designing a chemical looping system and I want to get, say, like ash particles out that are lighter than, say, carriers, right? Because I can just blow them out of that media. So even though it's fun, I mean, it's really practical stuff to know what happens to these systems as you operate. So I noticed for some reason that my slide did not print what's in red down there. I marked it in red. So you might want to just add UMF, the minimum fluidization velocity, and UTR, the transport velocity, are parameters that you'll hear a lot. And so you have to add enough gas to get you to the transport velocity. And if you add a sufficient amount of gas, you'll actually transport all the material out of the bed. Right? So they're very different regimes of fluidization. You can start with very smooth. You get to a condition where you add more gas. You'll see bubbles starting to appear. These start to break up, become very turbulent. And you end up with fast pneumatic, where you have a lot of turbulent energy carried up through the system. And finally, transport, where you actually carry the material up and out of the bed. And all these are used for different reasons in different applications. There are a couple of components here that you actually need to know about. You actually have valves that you put into these fluid bed systems, things like this loop seal. You can have solids flowing down at this region. You're fluidizing this whole bed. The bed fills up to this level and then spills over and then goes out of this region. and this becomes a seal between gases on this region and gases in this region, and you'll see how we use that in a chemical looping system. And then this device, an L valve, pretty common. If you add no fluidizing gas right here, everything stops, right? So it's a valve to turn things on and off, but also to control the flow rate. Because if I just start to add a little bit of fluidization, you'll get a slow flow rate around that corner because the media is actually interacting with the level of fluidization in this region. So you actually use this L valve to control how the material moves around the system. Different solid particles will fluidize in different ways. This is a major, major headache or advantage, depending on what you're trying to do. And I'm listing here the classification you can find in the literature for different types of solid materials circulating around these systems. And they make sense. Geldart classification A, you have this nice, smooth fluidization, very low density materials. If you have Geldart B, you'll get bubbles forming in that bed. As soon as you start to add the fluidization, the minimum fluidization velocity, you'll see bubbles. A, it will be smooth, you really won't see any bubbles. Particles that are classified as C, good luck. They tend to form clumps. This is extremely difficult if you're doing chemical looping combustion and you end up collecting a lot of fines. You can actually defluidize the bed and it becomes very unpleasant at that point because you got hot material sitting there forming a big clump of something that you can't get out. So you want to stay away from C. And D is things like trying to do coffee beans, right, or jelly beans. I mean, there's chemical processes where people actually fluidize things which are quite large, so you need a lot of velocity. They don't fluidize very easily, but they can be done so. So in a real system, you don't have just one particle size, one particle character. You got a whole bunch of them. This is why designing, if you know anybody who works in fluid beds, by the way, Princeton has a very excellent fluid bed research group here in the chemical engineering department. You've got to take your hat off to them because they're working a tough issue when they go to design one of these. Types of different gas-solid reactors. I'm going to just cover this in one more slide and then we'll take a break here. Fixed beds, you don't fluidize it at all. You might move a little bit of air through it, but it's basically sitting there fixed and you're moving the gas over these reactive particles. Bubbling, that's when you get, you're below the transport velocity, but you're above the minimum fluidization. Bubbling fluid bed combustor. Those things are built, that people make steam power plants out of that type of technology. Probably more commonly in a little bit wider use, circulating fluid bed reactors. Here you put in fluidizing air in this region of the combustor. It actually, there's a fluidization region here that's turbulent, and then you convect up into this region and then go through this cyclone, and the material just circulates around here. Most of that circulating material is bed material, not coal. I said before, like 2% of it might be coal. And so that rest of that material gives you nice uniform temperature all the way around while you're operating the system. It's a big thermal mass circulating through that system. So that's circulating beds. Moving beds don't necessarily need to be fluidized. And if you work in like gasification, there's a whole category of gasifiers built in this technology that are counterflow. Does great things for gasification. But since they're not fluidized, it's hard to get a uniform reaction rate through the system, right? And finally, in train, there's no bed at all. It's like dilute phase, like pulverized coal combustion. So it's typically called in train, some other terms used as well. So I lied to you because I want to show you the movie first. Now let's take a break, 15 minutes. We'll come back. It'll be a nice way to get started. We'll show you a movie of all the processes I just described. So back at 3:30.